Okay. Yeah, I think I'm recording.
Okay.
Yeah, so I will tell you about variational quantum eigensolvers and about complete pools of operators, how we build the ansatz with them. And but first of all, this is the plan that I'm going to follow. So first of all, I will give you a brief introduction into what quantum simulation is. Then I will tell you about the difference between digital and analog quantum simulation. Then I will actually give some introduction into what variational quantum eigensolver algorithm is and tell you about our work on ADAPT-VQE. And then I will tell you about complete pools of operators, about their algebraic properties, about other properties that they have. Also, I will tell you how we apply them to find the ground states of molecules and how symmetry is important when we deal with these things. So why do we need quantum simulation? That's basically because if one tries to describe the quantum particles, and for example, we'll have 40 speed 1/2 particles, then as a Hilbert space that we need to describe would be 2 to the 40, which is approximately 2012 numbers large. And this is approximately 4 terabytes of single precision numbers already, which is very, very much. So for example, for 80 spins, this is basically intractable on any computer that we have. And that's why there is an idea that goes back to Feynman that a quantum system should be simulated with another quantum system and not with a classical system, because then we can encode the state of our physical system into the state of our simulator. So how do we do it? For example, imagine that we have some state phi 0 of a physical system, and we evolve this state to some state phi t with an evolution operator u. So what we can do, we can basically prepare our simulator. Then we map the state of the physical system to the state of the simulator. Then we map the evolution, see how the simulator evolves, and then we just do the mapping back and understand in which state our physical system is, because we know in which state our simulator is and we can measure it. That's basically the idea behind quantum simulation. And what can we, when should we use it and what can we get with it? So of course we have to use it when classical computer breaks down. And this is usually happening for many body systems or molecules or for correlated materials where there is no good approximation that would allow us to treat particles independently. And what we can get with that, we can get as a static or dynamic property. So static would be, for example, the eigenenergies. Also, that could be some quantum phase transitions between different phases of matter, like superconductor to insulator transition, some mod insulators. Also, we could get all possible thermodynamical properties like entropy and derivatives of entropy, which basically tell us how the system reacts to heat, how it interacts with its environment, and so on. Also, for example, we could get dynamic properties like reaction rates, because what we can do, we can say, okay, two molecules collide and then either they react or not. And this is basically time evolution and what will happen after they interact. And basically, if we can model this time evolution, we can get these reaction rates. Also, we may be interested in some transport properties like heat conductivity, electrical conductivity, and in principle, all that for these complicated materials, quantum simulation would give us. It's important to understand the difference between digital and analog quantum simulators. I think it's quite similar to digital and analog computers that we know about. So a digital quantum simulator would be able to basically perform any gate. It would just decompose it into a set of elementary gates and implement it. And if we can do that, implement any gate, then we can simulate any system that we want and have the access to any property of this system that we want. This is basically a holy grail in the field, but still this is quite far. And the original Feynman's idea was that maybe we should use an analog quantum simulator. What we can do with that, we can just model the Hamiltonian of some particular system. So that doesn't mean that we will be able to model some other system. And that doesn't mean that we will be able to access all properties of the system that we model, but we can at least get something useful. And that's basically the idea of this analog quantum simulation. It's not universal, so one doesn't get all one could get, but at least one gets something. And what is a digital quantum simulator? So this holy grail. So this is, as I said, so this is a simulator that can implement any unitary, and basically it can do any quantum evolution. Given a state psi and a unitary u, it can implement u psi. And one of the famous algorithms that we would like to use this quantum simulator for would, for example, be a phase estimation algorithm. It says that if psi is an eigenstate of U, and then basically we apply it, we get e to the I alpha psi, we have to estimate alpha. By the way, if you have some questions or something that's unclear, just interrupt me during my talk, because I think this is totally fine and it will be better like this. So phase estimation basically says, please estimate this phase alpha that we get for an eigenstate of a unitary operator. And there are many ways to do it, which basically require different resources or a little bit different modifications of the algorithm. But the textbook thing that one can find, for example, in Chuang, for the phase estimation, it looks like this. So I will not go into details, but basically one needs this system that is prepared in the state psi, and then one needs the ancilla quantum qubits. So one first does this Hadamard gates on the ancillas, and then one has to apply this U many times controlled on the state of the ancillas. And that's basically where this property that we can implement any gate comes into play. And afterwards, we need to do an inverse quantum Fourier transform and then measure. And the promise is that after that, we will be able to measure, sorry, it should be alpha instead of theta. We should be able to measure 2 to the power of t times alpha. And if it coincides with one of the states in the bit representation, then we would get exactly this. If not, we will get something close to this. But one can really show that we can measure this alpha with a very huge precision using this algorithm. And that's basically the idea, but that's really hard to realize. And for now, digital quantum simulators cannot do this usually for interesting systems. But still, let's discuss how digital simulator would do this. So, and why is it so complicated? So very often this unitary is just generated by Hamiltonian. And in that sense, this alpha that we measure would actually be an eigenstate of the Hamiltonian. And basically, we want our quantum simulator to implement this unitary, this time evolution. But how do we do it? So one of the ways to do it would be a trotterization. So we say, okay, we want to implement this unitary, and it's very hard to exponentiate an operator and apply this unitary. So what we would do, we would split the Hamiltonian into the sum of local terms. Each of them can be easily implemented. Then what we would do, we would say a unitary is in this exponentiated form. And this u of delta t we will try to approximate. And there are many ways we can approximate it, but the most basic trotterization is just treating these HL terms as if they do commute. And then we just write it as a product of exponents. And because we neglected the commutators, we get some error, which is quadratic. And one can already see that this trotterization is a process as a trade-off between precision and the number of steps. So if, for example, the step delta t is very, very small, then t divided by delta t here is very large. But on the other hand, we get a very good approximation to each step, to each basically u of delta t. And that requires a really, really long gate sequence, but it will give us good precision. If, on the contrary, delta t is quite big, then this approximation is not very good. But on the other hand, the circuit is not that long. So this is a trade-off. And there are better ways to do this trotterization, or like not better, but other ways which could get some better results, like, for example, symmetrized version of trotterization, randomized trotterization, when one makes some random sequences of this exponents of this HL, and there are some approximate versions, but still this trade-off remains. And for the near-term quantum simulation, it's very hard because basically all the devices that we now have, they are not, they don't have the quantum error correction yet, so they are still quite noisy. And this long circuit that this trotterization requires, it would just be destroyed with, it would just basically be destroyed with noise. And still, one would like to use some quantum simulators because we know that even for 50 to 800 quantum bits, which is not much, the state would already be intractable classically. So we would like to be able to benefit from this already now, even though the machines are noisy. And how one would like to do it? So basically the idea is maybe we can somehow limit the role of quantum hardware. So not to put all the problem on this hardware, but just try to use it in combination with the classical hardware, and maybe that would give some result. And that's where VQE comes into play. So the idea with VQE is the following. Imagine that you have some reference state. It doesn't matter what it is for now, just some reference. And then you apply some unitary transformation to this state, which are parameterized with some parameter vector theta. Then one would get a state which is also parameterized with theta. And what one would then do, one would then construct the energy value, which corresponds to this state psi. So one would just measure and get this energy function with respect to theta. We know from a physics variational principle that the ground state of our system is always lower than any value that we can measure like this, that any energy for any theta. So that means that if we minimize the function E with respect to theta, if we minimize it with respect to theta, then the values that we will get will never be smaller than the ground state energy. And then if our parameters are basically explore enough of the Hilbert space, so if this psi of theta can be quite a lot of, can be basically almost everything in the Hilbert space or close to that, then we are sure that most probably we will get very close to the ground state, or if we're lucky, we'll even hit it. And that's basically what we would like to do with variational quantum eigensolvers. So we would like to minimize the energy and find the state psi, which minimizes it. And we would like to end up in the ground state, because if theta gives enough, if basically theta gives enough a big part of the Hilbert space, then we should be really close to the ground state. Yeah, but for that, if we would like to do it for some molecules, we would first need to understand how we should map our molecules on our quantum hardware, because we cannot just measure the energy for the quantum hardware and for the molecules. And also, what one has to understand why classical computer comes into play. So imagine that you don't have to measure this eigenset of energy. So this quantum measurement is not required. Then you would just have an oracle which gives you the value of the function E of theta. And in that moment, you basically don't need quantum hardware at all, because you say, okay, I have a function E of theta, and I just need to minimize it. And I would use any classical minimization algorithm. And for example, if I would need to compute the gradient with respect to theta, I would just measure, ask Oracle for the energy in 2 close points and compute this gradient. And then I would know how I should update my theta, and then ask Oracle for the value of the function again. And basically, that's the role of classical computer here. And what the quantum computer just does, it just acts as an oracle. So it basically just tells you, okay, you want a value of energy with respect to theta, I give you that. And basically you prepare the state on the quantum computer and you measure the energy on the quantum computer. That's all one does. And that's why the role of the quantum hardware is limited here. But again, as I said, one has to be able to map the states of the molecules and the Hamiltonian of the molecules to our quantum hardware. And I would like to briefly explain how one can do that. So imagine that we have a molecule. A molecule, one can think of a molecule as a system of interacting orbitals that electrons can occupy. And first, what one does, one uses some mean field approach. Usually it's a Hartree-Fock calculation that gives you some set of single particle orbitals. And usually what one does, one tries to find these single particle orbitals in such a way that if we would now approximate our solution with a single particle solution, just saying, okay, we neglect all the correlations between electrons, just say that one electron occupies psi1, the other psi2, and so on. Then we would like this approximation to be the best single particle approximation possible. So these mean field approaches, they basically give us such single particle orbitals that they cannot be made better in some sense with respect to energy. Only only including correlations we can make the solution better, but not changing the single particle orbitals. And once we have these orbitals, we can actually go to the notation which in physics is called the second quantization, where this quantum state of the system is represented as some set of creation operators which act on a vacuum. on a fermionic vacuum. So in some sense, fermionic vacuum is a state of 0 electrons, there are no electrons, and then this fermionic creation operators, they just create electrons in p orbital, then in m orbital, and then in l orbital. And that's basically how we can think of these quantum states. Then the Hamiltonian, after doing some transformations and rewriting the molecular Hamiltonian in the second quantization form, one can show that they actually take this form, which this is a kinetic, called the kinetic term, and this is called the Coulomb term. And again, the Hamiltonian looks like basically is written in terms of this creation and annihilation operators. So usually a dagger is creating an electron, A is destroying an electron. That's how this is basically the notation in physics. For example, if an A operator would act on 0 in this orbital, it would basically just give 0 as a result. And if a dagger would act on this 0 orbital, it would get 1. So that's basically the idea. And now one has to map the state of the fermionic system to the state of the qubit system. And here one does the following. So first of all, we say that the notation is the following. The number of orbitals is equal to the number of qubits. So 1 qubit per orbital. And then this electronic vacuum we map to 0, 0, 0 state of the qubits, basically. So this 0 string. That's the convention. And now what one has to understand that if we are somehow able to map this creation and annihilation operators to the operators that act in the qubit space, then we basically are done. We can map everything. So then we can map the states because they have this form, and we can map the Hamiltonian because it has this form. So all we need to do is just to map this creation and annihilation operators. And of course, we have to take care that this is a fermionic operator, so they anti-commute, and they after we rewrite them in terms of qubit operators, they should again anti-commute. Matrix elements of these operators, of course, should be conserved. Otherwise, it would not make sense. So it would not map a fermionic system, but map something else. So, and the way we can map it is not unique, but the one that is mostly used and the one that I will be telling you about, or like use in my work, will be Jordan-Wigner mapping. And so if you look here, so here are the operators acting in the fermionic space, the annihilation operators, and here are the operators acting in the qubit space. And in the qubit space, one usually uses X, Y, and Z and their superpositions, for example, Q. So these are the Pauli matrices. And basically one maps from annihilation operators to these qubit operators. And what one can see that, and basically here is also written how the state is mapped. And what one can see that the occupation numbers are actually mapped locally. So for example, 0001 of in the fermionic picture is just mapped to 0001 in the qubit picture. So just 1 in the qubit picture means that the state was occupied by the electron. So this is a nice thing about Jordan-Wigner, that we can basically map the occupation numbers locally. But then what happens is that because these fermionic operators, A, they are fermionic and they anti-commute, the qubit operators that they are mapped to should also anti-commute. And that's why one has to add these strings here to make sure that the fermionic operators have the right form. And that's why basically there are other mappings which you kind of try to make a trade-off. Okay, we won't map the occupation numbers locally, but then we won't have such long strings here to account for this anti-commutation of the fermionic operators. But that's basically the details. For now, we are only interested in Jordan-Wigner. And once one has this mapping, one has to understand that one doesn't need to distinguish our original fermionic system and the qubit system. So now, in terms of after this mapping, it's basically the same. And Hartree Fock would basically correspond to a single particle state. So when electrons just occupy some orbitals, and we neglect the correlation, so it's just a classical state, and then it would just be mapped to the with the Jordan-Wigner as it is. So just for example, for 4-electron problem in 12 orbitals, this is just like this. So for ones and then 8 zeros. And now we basically have all the things to realize variational quantum eigensolver. So we know how to make the encoding, we know how to build the oracle, how to build the energy function, we know how to apply gates. So we can basically do the algorithm. And what's very important to understand, it's very important which ansatz one chooses. What is this operator T of theta, which basically transforms our reference state? And there are really many ways to approach it. So one of them is basically problem agnostic ansatz, which in some sense don't care about which problem we solve. So they would just use the same set of parameters, the same parameterization for each problem and try to solve it. And the most famous of these approaches is unitary coupled cluster, which basically tries to apply first like single particle fermionic excitations, then it applies this longer strings, which are basically double excitations and so on, and hope that after some steps, algorithm will converge to the ground state. And it has some advantages because it's basically these fermionic operators, these generators of these unitaries, they are inspired by nature. So this basically, these are really fermionic operators in terms of which the Hamiltonian of the system is usually written. And that's why it theoretically behaves well. But unfortunately, when one starts to realize it, it turns out that it requires, basically when one really wants to map it to a quantum machine, one has to use the gates which are native to quantum machine, and then transpiling to these gates is very inefficient, so it's complicated to do. And also sometimes these long strings are very hard to realize, so one has to trotterize somehow as well. And then there are other problems that I told you with factorization before. And basically that's why basically this is not the most like used approach to my knowledge. And another way would be to use the hardware efficient ansatz, which basically try to parameterize the solution with the gates that are native to the quantum machine. And they basically aim to minimize the C0 count, so to make the gates not too long and to be able to realize it on a noisy machine. But then it has also disadvantages. That, for example, nobody proves that this is exact. So these are just random gates which are good for the machine, but who knows if they are good for the actual ansatz and for the actual system. So we're not sure. And also there are things like barren plateaus there when one starts to increase the layers, and basically the solution doesn't improve. And that's why, but still, like with this approach, IBM, for example, could make the proof of principle for these simple molecules like H2, lithium hydrate, beryllium H2. So they really managed to use this hardware efficient ansatz to actually see the dissociation curves of these molecules. Another idea would be to use problem tailored ansatz, which actually care about which problem we are trying to solve. So they don't use the same ansatz for every problem, but actually try to get some knowledge, some information from the problem. And the most famous ansatz like this are QAOA and variational Hamiltonian ansatz. But there are also others. And for example, I would like to tell you about this novel algorithm, which is called ADAPT-VQE, which we are working on at Virginia Tech. So ADAPT-VQE starts with a concept called operator pool. So operator pool is just a set of operators that we are going to use to build our ansatz. So we have some a number of operators, and what we do with this algorithm is the following. We initialize our state in the Hartree Fock, for example, so in some reference state. Then we select an operator from the pool. And the way we do it, we actually measure the gradients of energy which this operator would give us. So we measure these gradients for all operators and choose the one that would give us the biggest gradient for the energy. And that's the operator that we hope would basically improve our solution the most. We pick it. Then we basically take the solution on the previous step and just multiply it by the exponent of this new operator that we chose with some coefficient alpha, which is initialized to 0. Then we basically construct this energy function, as I showed you before, and try to optimize with respect to all the parameters to get the minimum of energy. And that's our new state. Then we go again to this place, choose one more operator, and everything continues. And we basically add these exponents until we converge. And the first realization of this algorithm was a fermionic adapt. So this operator pool was using fermionic creation and annihilation operators. So it was basically using single qubit excitation, single particle excitations, which are A dagger A, and 2 particle excitation, which contain basically 4 operators. And if one computes how many such operators there are, then it turns out that this number scales as n to the power of 4 in terms of the number of qubits that we have. So, which is quite a lot. And also it has disadvantages of all basically hardware inefficient ansatz, that it's hard to transpile this to native gates of the quantum machine. That's why there was an idea that maybe we should just split these fermionic operators into the basic Pauli operators, Pauli strings, which are more native to the quantum machine. And that was basically the idea behind qubit adapt. So now our operator pool is just a set of some Pauli strings, and each Pauli string just looks like this. So it can be, for example, x, y, I, z, and so on. Each of these operators acts on the corresponding qubit. So, for example, this one acts on the first one, y on the second one, I on the third, z on the fourth, and so on. So this is a more hardware efficient pool, but still, because we constructed it from a fermionic adapt, it still scales as n to the 4. And here where my challenge comes. So imagine that we would like to decrease this number. Then if we take too few operators in this pool, then ansatz will never converge, because we will not be able to explore enough of the Hilbert space to come close to the ground state of the system. But if we take too many operators, like n to the power 4 or maybe even more, then we will have this huge measurement overhead that we have to measure the gradient on each step for each of the operators, which is too much. And basically the challenge that I was working on was to find the minimal number of Pauli strings in the pool so that the ansatz would converge. And basically that's the idea, and mathematical formulation would be the following. So we have some Pauli strings, k Pauli strings, and they form a complete pool if for any states phi and psi, we can basically transform one to the other using this ansatz. So we would be able to have some finite number of these exponents that would transform phi to psi. And for example, then we would say, okay, phi is our Hartree-Fock reference state and psi is our ground state. And at least we know that the path exists with this pool. Of course, the question of whether ADAPT will find this path or not is a different story, but at least we know the path is there. And also, because we're working with molecular Hamiltonians, and they have time reversal symmetry, then basically the states of these molecules can be represented by real vectors. So that's why we basically map real vectors to real vectors with an orthogonal matrices. And then basically to get an orthogonal matrix here, one has to allow only for imaginary Pauli strings. Then multiplied by imaginary alpha, that would basically give us a real matrix. So that's why we only limit ours to imaginary or odd Pauli strings. And what basically two objects that follow with the pool are, first of all, the Lie algebra that can be generated through all possible commutators of these operators. And then it's a Pauli group. So it's basically all possible products of Pauli operators. And from the theory of Lie groups, we know that completeness is determined by the size of the generated algebra. So if the generated algebra is big enough, then we can find this mapping. If not, then we cannot. And mathematically, that means that what is the minimal number of generators of the algebra that is big enough to transform any state phi to any state psi? And here, a nice property of Pauli strings comes into play, that two Pauli strings either commute or anti-commute. So if they commute, then the commutator is 0. But if they anti-commute, and we compute a commutator, then actually this commutator is equal to the product of these Pauli strings. And what it means for us, it means that algebra is actually a subset of the product group. And if we first analyze the group, we can actually say something about the algebra. So if our group is too small to host enough operators to make this transformation from phi to psi, then our algebra is too small as well. And working with the group is a lot easier. And that was basically the idea that we used. So first of all, one can notice that the operators from the Lie algebra and from the Pauli group must be able to flip any set of qubits. So what it means on the example of 2 qubits, that means that basically we have to be able to flip 0, 0 to 0, 1, 0, 0 to 1, 0, and 0, 0 to 1, 1, which means that we must have either IY or ZY, either YI or YZ, and either YX or XY. So basically, because X and Y, they flip the qubits, and I and Z, they don't flip the qubits. So if we don't have, for example, we have neither YX nor XY, then we will never be able to transform our 0, 0 to 1, 1. And that means that this condition that we can transform any state to any other, it already breaks, because we cannot transform 0, 0 to 1, 1. So we are sure that we must have all these operators. And already from this condition, we can show that the minimum size of the pool, so the minimal number of Pauli strings that we will need, is bigger than 2n minus 2. If it's smaller than that, we will never be able to have enough operators here, and then we will never be able to transform any state phi to any state psi. But also, we show that if the equality is reached and our pool is a minimal complete pool, then we even know what the product group is that we are actually generating. So we know that this group is generated by these generators that I show here. Then we also show that at this point, when k is equal to 2n minus 2, these two conditions are actually equivalent. Then we basically derive the necessary conditions of completeness, but who said that actually such condition can ever be realized? Maybe there is not a single pool that would have size 2n minus 2 and would be complete, even though the necessary conditions are derived. For that, we actually construct a protocol that can transform any real state to any other using a well-defined pool of size 2n minus 2, and we show and we prove that it works. So I will only show you the example for 2 qubits. So for 2 qubits, you have all 2n minus 2 is equal to 2. So we only have 2 operators, which are z2, y1, and y2. Well, here I number the state. I have the notation as the following goal. So I want to transform the superposition state of 2 qubits to arbitrary superposition of the 2 qubits. One has to understand that here it's a bit, instead of alpha and beta, I basically use this. I basically just say that, okay, I have some E1, which is a real vector for the state of the first qubit, and E2 is also some real state of the first qubit, and this is basically the entangled state of 2 qubits. So the qubit on the right is the first qubit, this qubit on the left is the second qubit, and this is basically the entangled state written in this form of vectors, basically, so without the coefficients. But of course, this state is normalized as it should. And the protocol that would transform any state to any other is the following. So the first step that we do, we would apply the exponent generated by y2. And we can show that after this transformation, we can actually bring it to a state in which the length of u1 will be equal to the length of u2. So we basically did a transformation on the second qubit in such a way that the length of the states of the first qubit, u1 and u2, became the same. So they might not be the same in the beginning for e1 and e2, but they will be the same after this step. Next, what we do, we apply this second operator, the unitary generated by the second operator, and one can visualize the evolution that happens on this vector 0, u1 plus y, u2. So what happens, basically, z2 acts on 0 and 1, given plus and minus 1. And that means that for u1 and u2, we have rotations in different directions. And because the lengths of these two vectors are the same, there is some value of alpha when they will coincide. And this, at these values, they will point in the direction of some vector u. The next step that we do, we would again apply the generator of y2 and basically transform this state to 0u. That we can do because basically we just transform 0 plus 1 to 0. This is essentially a Hadamard gate. And the fourth step would be to apply this one again, and then we can transform 0u to 0, 0. And now we basically, what we did in these 4 steps, we transformed this arbitrary state of 2 qubits to 0, 0. And if we can do that, we can of course do the inverse and use the inverse steps of this protocol to transform 0, 0 to the target state that we want. And this is how we basically show that the pool exists. So for 2 qubits, this pool exists. And we show the product by presenting the protocol that the transformation is really working. And then we use induction to prove that there is actually a pool for each number of qubits that do it. It has 2n minus 2, and this 2 qubit cases uses an induction basis. And for each number of qubits, one can actually show that indeed up to the renumeration of qubits, the pool constructs the right group that we derived before for the necessary conditions. And also one important thing that one can show that the algebra spanned by this pool, it always spans all odd strings from the group. So the Pauli group, of course, has both odd and even strings, so not only real power, not only imaginary Pauli strings, but it turns out that the algebra spans all possible imaginary Pauli strings. So of which there is this number. And there are many reasons why this pool is not the best pool to use in actual simulations, but it's actually good to prove that the concept actually works, so that such pools actually exist. And the fact that the algebra spans all odd strings from the Pauli group actually gives us the first sufficient conditions of completeness. So if we assume that the strings generate the right Pauli group, then if the algebra also spans all odd strings from this group, then we are sure that our pool is complete. So in some sense, by just computing the algebra and comparing its strings to the odd strings of the Pauli group, we can already say, okay, our pool is complete. But unfortunately, computing the algebra for these generators takes very much time, even for 8 qubits. And that's why we had to derive one more condition, which follows from the completeness. And this is the inseparability condition, which means that if we have a pool and this pool is complete, then we cannot split it in 2 groups such that every operator of one group would compute with every operator of the other group. So basically, like 2 mutually commuting sets. So this can never happen, which basically we refer to as a property of inseparability. And the nice thing is that for now, we also numerically proved, we don't have an analytic proof yet, so we are still working towards this, but numerically we see that basically from these inseparability conditions, provided that the right group is generated, it follows the algebra spans all odd strings from the group. So in some sense, these conditions are actually equivalent. And one can use this inseparability together with the structure of the group to actually act as a criterion of completeness. So in some sense, and this is very nice because this inseparability takes like the n squared, the computational complexity is like n squared in the number of qubits. So we can check it instantly and use it as a criterion of completeness. So if we get a pool, we can very quickly test that this is complete. We still need, of course, to generate the group, but it's not that as hard as generating the algebra. Well, that's nice. So we have sufficient and necessary conditions of completeness. We have criterions, but still, when we try to apply our pools to actual physics problems to simulate, for example, 8-qubit H4 molecule. So H4 like has 4 H atoms, so it has like 4 active orbitals, which are mapped to, because of the spin, which are mapped to 8 qubits. So 4 spatial orbitals means 8 spin orbitals, and they are mapped to 8 qubits using Jordan-Wigner. And we start in the 4-electron Hartree-Fock state, which is a half-half filling. So we have 4 ones and 4 zeros. And again, we will grow the ansatz one operator at a time based on the energy gradient. And what happens that either, for most complete pools, either ADAPT doesn't start or it exits before convergence. And the problem actually happens on this stage of measuring gradients. So all the gradients are actually 0 for most complete pools, even on the first step. And of course, this cannot be a coincidence. There should be some explanation to this. And the explanation is symmetry. And I will first try to tell you about why ADAPT doesn't start. So that basically means that we have our reference state, which is usually Hartree-Fock state, and the gradients are 0 at Hartree-Fock. So to understand why, one has to draw the sketch of the molecule and look at its symmetry. So we can basically, first of all, say that each orbital has an occupation number. So it's, for example, the ones are occupied by the electrons, the zeros are not. And each electron here has a spin. So when the orbital is occupied, we have a spin which is up or down. And also the spatial orbitals that I draw below, they have a parity because we have a mirror symmetry, like inversion symmetry here. And that means that our spatial orbitals are also parity symmetric. So they have either positive parity or negative parity. And it turns out that parity, spin, and the number of particles are good quantum numbers, which means that, for example, So first of all, the basic thing about Hartree-Fock, that single particle excitations are forbidden. So, for example, one cannot just destroy an electron here and create it here. This is forbidden by this operator. So this operator will get a 0 gradient because basically, as I told you, Hartree-Fock is already optimized to be the best a single particle solution. So if we would have some energy gradient at Hartree-Fock, that would mean that we could just make some other single particle orbitals, which would be combinations of our orbitals at this moment, and then we would get some better solution. But this is not possible, and that's why the gradient at Hartree-Fock for single particle excitations is always 0. And this is an example of operators that would give a 0 gradient. But apart from that, we have to conserve the symmetries. And for example, we have to conserve the number of particles. So if we try to destroy an electron and just bring in this state from 4 particles to 3 particles, this is forbidden. Also, we are forbidden to change the spin. For example, this operator, it would conserve the number of particles. So it would destroy the 2nd electron and the 4th electron and create the 5th electron and the 8th electron. But one can show that actually the spin would change. And this is not allowed. And that's why, because you destroy 2 spin downs and you create 1 spin up and 1 spin down. So the spin would change, and this is forbidden. And that's why this operator has a 0 gradient. Also, one is forbidden to break the parity. So for example, one can show that this operator, it conserves both the spin and the number of particles. So it would destroy the 1st and the 4th electron, but it would create the 5th and the 6th electrons. So the number of particles would be conserved, the spin would be conserved, but we basically promoted an electron from minus orbital to plus orbital, changing the parity of the state. And this is forbidden. That's why the gradient of this operator would be 0. Also, one can show that operators that have more than double excitations are forbidden because of the structure of the Hamiltonian. So our Hamiltonian only has a single and a double particle excitation, and that's why it will never be able to have a gradient for this kind of operator. And these are basically all the conditions. So we really, for 8 qubits, it's still possible. So we really just assembled all the operators that break these rules, and we show just that every operator has a 0 gradient, and all others that basically do not break this rule, they all have non-zero gradients. So in order for ADAPT to start, one just has to provide enough number of operators which would obey these rules, and then ADAPT will start. But then what to do with ADAPT stopping before it converges? So this is actually another problem. It's related to symmetry as well, but it's a bit different. And what one has to understand that, for example, for H4, particle number, spin, and parity are good quantum numbers for Hartree-Fock state and also for our ground state. And they're actually the same. So what happens that we try to bring our state from one state in some symmetry subspace to the other state in some symmetry subspace. And basically, we would like to do it, they lie in the same symmetry subspace. But if we start to apply ADAPT, if we start to apply ADAPT, so for example, we take this operator, which has a non-zero gradient, and it would take us from Hartree-Fock to this superposition. Then we would take this operator, which also has a non-zero gradient, and it would take us to a superposition which already has, for example, 4 electrons. So in principle, during the after the second step, we can actually have quantum numbers which are different from those that would be for Hartree-Fock and from those that are expected for a ground state. So we can really have a superposition of 8 electrons, which eventually will, after many steps, this epsilon will become very small. But still, during the operation of our algorithm, we can have states which break the number of particle symmetry, and the same for spin, and the same for parity. But what one can notice that operator can never be picked if, for example, it would change the number of particles not by an even number but by an odd number. So we can have six particle states, we can have 8 particle states, but we will never have 3 particle states or 5 particle states or 7 particle states. And the same applies for spin. So what happens that one can show that the gradient-based criterion can only pick those operators that are changing the quantum numbers by an even number of quanta. And basically, our complete pools actually were designed on the contrary to be able to transform any state to any other. That means that they must contain operators that would take us to, for example, 3 particle states, because when we say any map to can be mapped to any state, we also mean states outside of the symmetry subspace. So in some sense, we want to push our state from one point in the symmetry subspace to another point in the symmetry subspace through a path which lies outside of the symmetry subspace, and ADAPT can never find this path because these operators are never picked due to a gradient criterion. And basically, our complete pools, generic complete pools, will always contain operators that will break this rule that the number of particles can be changed by an even number of quanta. How we approach this problem, what can we do? So first of all, let's describe what we want. So psi here is a ground state that we want to achieve, and Hartree-Fock is our initial state. And the transformation, in principle, can look like this. So that would be some unitary, which is an exponent of a superposition of operators from the Lie algebra. So all possible operators, and these operators, they of course lie inside of this complete pool generated by they lie inside of this complete group and algebra generated by our complete pool in principle. But on the other hand, apart from being in this, A operators have to be replaced by these commutators. I'm sorry. So these commutator operators, they are in the algebra, of course, in the algebra generated by the complete pool, but at the same time, they must obey these symmetry limitations that basically they will take the Hartree-Fock, which is a state of a well-defined spin number of particles and parity. They will take us to exactly the state which has the same quantum numbers. And which means that we don't have all possible operators here, but only some in this superposition, not all algebra operators, but only some. And what we can do, we can say, okay, let's restrict our group and algebra to operators that change quantum numbers by an even number of quanta, because we know that these operators that we need are actually also part of this algebra and of this group. So all other operators are not here because they would not take our state to the right to the other state of the right symmetry. And then basically we don't need such a big group which the complete pools generates us. We can just get a smaller one. So when we restrict the group and algebra to operators that change the quantum numbers by an even number of quanta, for example, for 8 qubits, it means going from 16,384 elements in the group to only 2,048 elements in the group. And for the algebra, we go from 8,256 to 992 elements in the algebra. So here it should be in the algebra. So basically, that means that now our group is restricted, but it still contains all the Lie algebra operators that we need for our gate, for our generation, for our path, basically. And now we know that, again, AKs are just commutators. So now we know that they are contained in the restricted algebra. And what we can do, we can just choose a pool that would generate this group and this restricted algebra. So basically, we now choose a pool that has this symmetric limitation, so that doesn't choose elements, that doesn't create elements that would change our quantum numbers by an odd number of quanta, but only would choose the right number of quanta, the even number. And if we do it, one actually can show that it really works. So for H4, for example, we can get a dissociation curve in about 30 steps with a minimal complete pool. And for the lithium hydrate problem, we can get it converges very fast. 8 qubit lithium hydrate converges like in 10 steps. And it's a bit harder for lithium hydrate because it doesn't have an inversion, but it has reflection planes, and they have to be included, but it's possible, and we get the results. So what we want to do in the future, so our plan would be to, first of all, finish the proof in inseparability criterion. So we are basically on the way to do that. Or we have to build a counterexample, but most probably it's not going to happen. Then, as I told you about the symmetries, I told you it more like hand wavy. So here we have parity, here we have some number of particle symmetry, spin symmetry, but it would be good to be able to describe this thing based on the irreducible representation of the molecular symmetry point group. So for every molecule, we would say, okay, we have the molecule, it has some symmetries, and then based on the symmetries, we can say which pool we have to choose. And also another direction that we work in, it would be an extension of minimal complete pool. So in some sense, a minimal complete pool can already explore enough of the Hilbert space to give us a ground state, but maybe it would do it much faster if we add some number of operators to it. So what would be an efficient way to extend these minimal complete pools to get to the ground state faster? And with that, I would like to leave you with my summary, and I would be happy to answer your questions if you have some.
All right, great. Thank you for speaking to us today. Does anybody have any questions?
I have a question. So how long have you been working on this particular problem?
Well, I've been working like since March, last March approximately, so like for approximately 1 year.
Yeah.
But
Okay.
I was working like remotely, so yeah.
Yeah. So what did you have access to any actual devices, quantum devices that you could use?
No, we didn't do it yet. So in principle, one can access the IBM devices, which are like available to the public. And
Yeah.
this was probably be something that we would do in the future. But for now, this is really like proof of principle work, which is like laying the foundations for the algorithm in some sense. So the idea was to actually be able to find these pools, to be able to prove their completeness, to have the codes that would test it efficiently. And basically, then we could, for example, also ask questions, okay, we have a quantum machine which has some connectivity. And then for particular connectivity, one would want to make the pool such that it would be native to this quantum machine. Because, for example, not every string, not every arbitrary string would, for example, be native for the machine. So we have, for example, this pool, but we don't know if, for example, the IBM device can very easily realize each of the strings, for example. So in principle, the idea would be maybe to try to tailor our pools to the machine. So actually there are many complete pools and we know how to test them. So we could just choose the right ones and just take the one that would be complete and use it. So yeah, that's also the future direction, which you didn't show.
Okay, thank you.
So do you have the problem of barren plateaus when you have your have the pool of operators still?
I didn't face it, but honestly, I only worked on H4, H6, and lithium hydrate now. So I think I had some numerical problems with H6 because it has 12 qubits and I was just running it on my laptop. And after like 1 week of simulations, I didn't converge yet, but it was getting better, just too slowly. So it's limited by classical simulation. So I didn't see barren plateaus there. So I would definitely see that the error goes down steadily. It's just that for 100 iterations, I would already have to wait for like 2 hours for each consecutive iteration. So I'm planning to do it on the cluster and see if it actually converges to the good precision. But for now, we didn't see any barren plateaus with this. Yes.
Okay, thank you. All right, does anybody else have any other questions?
So this potentially can extend to more molecules and more simulations, right? I mean, you told us about these few molecules that you are simulating, but the same idea can extend to others, I guess.
Yeah, of course, like we would like to be able to apply it to more complicated molecules because, of course, like 8-qubit molecules, one can just diagonalize the Hamiltonian like in a matter of a second on a laptop and not use any quantum algorithm. So this is just really proof of principle. But of course, one would like to go to more complicated molecules because, for example, I think like maybe around 20 orbitals, it's already close to the limit. So it would still maybe be possible to compute it on some device which would be tailored to that, but it would definitely be a very complicated classical simulation that one would have to work on. So it's not something that one would write a program in Python and it would just run. So in principle, we're not talking about hundreds of orbitals or qubits here. We're like talking about 20, and that would already be something really, really challenging to try. So I don't know how fast we will get there, but yeah, so first I have to finish H6.
Very nice work.
Thanks.
All right, so let's thank Vlad for speaking to us today. Thank you. All right, so let me myself host again. Reclaim host. Here we go. And I guess, let's see, so you'll probably have to, so since I don't know how to use Zoom apparently, you'll have to stop recording on your end. So sorry about that.
Yeah, I stop recording. I hope it saves, because if it doesn't, I will be very upset. So